we are trying to prove concentration inequality, not just for sums of independent variables, but for more general functions, namely Lipschitz functions. Okay, so I recall what we want to prove and where we are in the proof. Okay, so this is this and it's Gaussian concentration, so it's really about Gaussian random vectors. So Gaussianity is important, we will see. Okay, so the setting is we have a function from Rp to R, and this should be a Lipschitz function, and a Lipschitz function has a constant, so this is L. Okay. Yeah, and then we apply this function to Gaussian random vectors, and we consider standard Gaussian random vectors. So our vector x has a distribution, which is a normal distribution with mean 0 and covariance matrix identity. So this just means all the components of this vector are independent, and each of them has a standard Gaussian distribution. Okay, and then we want to prove deviations of the value of the function from its mean, that this is, we can estimate large deviations are somehow small. So for all alpha bigger than 0, bigger or equal, we want to prove that the probability that of the vectors such that the distance between f applied to this vector and the expected value of this function, that this distance is bigger than alpha. We want to see that we can estimate this by 2 times exponential minus alpha squared divided by 2L squared. So the alpha is the deviation and L is the Lipschitz constant here. Okay, so I mean this is saying somehow that this deviation has a kind of Gaussian behavior. I mean this is the behavior of a Gaussian distribution. Okay, this factor 2 here comes from the fact that I have here an absolute value, which means I should estimate in 2 directions. Each of them gives me the same, and the same will be this one. So that's really what we are going to prove. And of course we also can assume that the expectation is 0 by just shifting things. So essentially we have to prove the probability that f is bigger than some alpha against this here. Okay. And then we also said we can assume that our function is smooth because we can approximate otherwise. So we can assume the Lipschitz condition can be then said that okay, our function is differentiable and the gradient of the function is bounded by L. Okay, and the idea of the proof is the same as in all those concentration estimates, namely we use Markov inequality, but we apply it to e to our function. Okay, so what we really have to estimate is the expectation of the exponent of lambda f of x. Okay, because then we apply Markov to this, and the lambda is a parameter which we choose later in order to optimize what we get. Yeah, and okay, and up to this point that's the general strategy, but now we have to use our specific situation. And the first step is that actually here this we estimate against a quantity where we replace f of x by f of x minus f of y, where y is an independent copy of x. Might look a bit strange, introducing extra information in the whole thing, but the point is, because our Lipschitz condition is essentially something on a difference of the function between 2 points. So we should be able to argue with such a thing. Okay, so we estimated this, and this was Jensen's inequality, that we could say that this is, or maybe first of all, we estimated this by the same quantity where I take the expectation of the exponential function, and then I have here lambda f of x minus f of y. And this was a trivial estimate. Essentially, it was because by Jensen we could estimate the expected value of the exponential of this guy by 1. Okay, so introducing this is not really doing much. It seems as if we haven't really done anything. But now the point is that this quantity here, this is something which we can control. I mean, it's hard to say something directly about f of x. Okay, but this difference we can control, and this we are going to write. I mean, we should control it in terms of the derivative of our function, because that's where we have control by our Lipschitz condition. And we are writing this just by the fundamental theorem of calculus as the integral over the derivative of its function. I mean, this is the function at the point between the point x and the point y. So this is the same as the integral over the derivative of the function at the 2 points. Okay, and we do this by taking, let's say, this derivative of this function, where we have a function which interpolates between x and y. The argument should now interpolate between x and y, and we do this in a specific way by taking linear combinations of them. So we take the cosine theta of y plus the sine theta times x, integrating over the theta. Okay, and if theta is running between 0 and pi over 2, I mean this guy here is running between x and y. For p over 2, it is x, because then this is 1 and this is 0. For 0, it is y, because then this is 1 and this is 0. Okay, and I have the integral over the derivative, so this means I should take the difference of this function at those 2 points, and this is exactly this. So this is just a very complicated way of writing this, but why am I doing this? Because it has the advantage that maybe I call this here x of theta. Nur rein. Kein Problem. Okay, so x of theta, and then the derivative of this by the chain rule is the gradient of this applied to the derivative of this guy. So what I have here, this here is the gradient of f at the point where I am, so at the point x of theta. And this is good because we have control over this. But then this is multiplied with the inner derivative. And if I take the derivative of this with respect to theta, okay, let me write it like this, x prime of theta. Good, okay. And now the point is that this x prime of theta I can also control very easily, because I mean this is of course is the same kind of combination, but I get the minus sign and here the cosine. Okay, and the point is that this and this are still a pair of independent Gaussians. Okay, so this is really something where I have good control over. Okay, the first thing I'm going, just recall or check that indeed this is okay, that x theta and x prime theta is really a pair of independent Gaussians. That's a basic property of Gauss, and this is a property which only works for Gauss. That's the reason that this whole proof here is really one which goes for the Gauss distribution. Okay, so I think that's where we stopped last time. Of course, we will continue here, but maybe first let me check or make precise that the x theta and x prime of theta are, for any theta, independent Gaussian variables. Okay, and maybe I'm doing this in the next lemma. Also, okay, I consider, as I have it here, x and y, 2 independent standard Gaussian random vectors. X and y be 2 independent standard Gaussian random vectors in R to the P. Okay, and then I take those linear combinations for any theta. So for theta, okay, in principle I'm running between 0 and pi over 2, but of course I can take any theta in R. Consider, so x of theta is what I have here. So that's a linear combination of y and x, where I take cosine theta of y plus sine theta of x. And then the second vector which I take is the derivative of this, but now let me just call it y. It's another combination, which I call y of theta. But it's the derivative of the first guy with respect to theta, so it's minus sine theta y plus cosine theta x. And this is x, the derivative of the first guy, but this doesn't play a role. I mean, here I'm not, I just fix a theta here and argue about this. But later, of course, it's important that this is exactly the derivative of this. Okay, and then I'm claiming that for any theta now, those two vectors together are essentially the same as before. Namely, it's a pair of independent Gaussian vectors. So then, for each theta, the two vectors, so they are still random vectors in R to the P, x theta and y theta are also two independent standard Gaussian random vectors in R to the P. Okay, I mean this is quite easy. Maybe you have seen this or this is clear, but still let me give the proof. So just that we are sure about this. And in principle, I mean what I'm doing here is I have two vectors, and if you're just thinking of x and y as being vectors, then essentially being independent is like they are orthogonal, and then I'm just rotating them by angle theta, and then they are still orthogonal, and their length is the same. I mean that's what's more or less in the background. So I mean, if I have here x and y, then essentially if I take a theta, then I'm rotating the whole picture. I get here x of theta and y of theta, and they still are orthogonal, which then means independent, and their length has not changed, so they still have the same distribution. Okay, but maybe let us make this a bit more precise. Or maybe let me first make as an example, specific choice for theta. If I take theta 45 degrees, then of course I'm talking here about the sum and the difference of two vectors. So maybe just to make it even more concrete. So if I take theta pi over 2, then this says that if I have two vectors, x and y, and they are independent, and each has a normal distribution in p dimensions, but this is also, you can also just think about p equal to 1, so it's just two independent Gaussians. And then if I'm looking on this combination, and in this case this is just x plus y divided by square root of 2 and x minus y divided by square root of 2, then this is again a pair of independent Gaussian vectors. So those guys are also independent N0, 1p random vectors. Okay, and so this will be very crucial for this proof. Okay, and so you might think, maybe I could generalize this to distributions which have the same property, that for example, if I take the sum and the difference, they are still independent, have the same distribution, but more or less this is a characterization of Gauss. So it's, I mean, if you have independent vectors which have some distribution, and the sum and the difference is still independent and has the same distribution, then it must be a Gauss distribution. Okay, so there is no no way of generalizing this proof here to more general distributions. It's really precisely a property of Gauss which is used. Okay, but anyhow, but this is of course a very nice and strong property. Good, but so let us look a little bit in the proof of this lemma. Maybe make this rotation thing a bit more precise, because we know, in particular from one of the assignments, quite a bit about what happens with distribution of Gauss under rotation. And so, of course, I mean, what we are doing here is, I mean, we have two vectors in R to the p, and of course, this means essentially if we put them together, we have a vector in R to the 2p. Okay, so I mean, I can look on the pair xy. So this is a vector in R to the 2p, and then this is of course again a Gaussian vector, namely, so this has a density, so psi of xy. What is the density of this guy? Because x and y are independent, it's a product of the densities for x and for y, and each of them is a standard Gaussian random vector, so we know the density is given by 1 over 2 pi to the p over 2 for the x. So namely then the density is e to the minus the length of x squared divided by 2. That's the the density, probability density for a standard Gaussian vector, and then the same for the y. 1 over 2 pi p over 2 e to the minus y squared over 2. Okay, and of course, I can also write this as 1 over 2 pi, and I have it p over 2 and p over 2 times, so altogether I have to the power p, and here I have e to the minus x squared plus y squared divided by 2. Okay, and this, of course, I can also say, I mean, this here, I mean, x and y are vectors in R to the p, but if I think of them as being vectors in R to the 2p, of course, this here is exactly the length squared of the vector xy. So this, I can say, this is 1 over 2p, 2 pi to the power p, e to the minus 1/2, and then I take here my vector in R to the 2p, so the vector xy. Let me write it as a column, so the square of this. Okay, so this is the length in R to the 2p, and those are the lengths in R to the p. Okay, and now I see, of course, so I have now the vector xy, I have now the density for this, and again, this is exactly of the same form as I have it for a standard Gaussian random vector in R to the 2p. So this is telling me that this vector xy, so if I put x and y together as a vector in R to the 2p, has as a distribution n0, and then the identity matrix in 2p. Okay, I mean, this is kind of trivial. I mean, I have a vector where all the components are independent. Each has a Gauss distribution. I have another vector with the same property. And if the two vectors are independent, this means the components here are independent from the components here. So if I put them together as a 2p vector, then of course I have 2p independent entries, and each of them has a Gauss distribution. Okay, so this is just writing this down, maybe a bit more formal, so this should be clear. But now, I mean, in this, if I really view my pair of the vectors as a vector in R to the 2p, I mean, then this replacement going over from xy to x theta, y theta is really a kind of rotation in this space. So okay, so the replacement, so going over from xy to x theta, y theta. So this is actually a unitary transformation in R to the 2p. All right. Be more precise. Actually, it's a transformation which acts separately on each of the components of my vectors. So essentially it's a transformation in R2, but applied to all the components of my vectors. So namely the basic transformation is the one which is there, namely the 2 by 2 matrix cosine theta sine theta minus sine theta cosine theta. So this is a 2 by 2 matrix. And if I also write maybe now my vectors in terms of components, so x theta, the components of this I call t's, so t1 up to tp, depending on theta everything, and the same for the y, and there I call the components s, so s1 theta up to sp theta, and then, okay, then I mean this vector here would be first all the t's and then all the y's, but in order to write it more nicely, I prefer to rearrange things so that I iterate. So first I took the first component of the y, of the x, and the first component of the y, and then the second component of the x, and then the y. So I'm writing this here in the form, this is t1 theta, and then I'm taking s1 theta, t2 theta, s2 theta, and so on, up to tp theta, sp theta, just a reorganization so that I can write the u in a better way. And then I'm applying, I mean this vector I'm getting by applying the amplification of this u to my basic vector. So this to my vector where the theta is equal to 0. So I'm applying this to t1, s1, t2, s2, and so on, up to tp, sp. Where this is the vector x and y. And what do I apply? I mean, essentially, for each of the component, for the kth component, I take exactly this linear combination of the kth component of the x and the kth component of the y. So which means for the first components, I apply this u. So this u is a 2 by 2 matrix, which acts just here. Then for the second components, I also take the u, so acting on the second components, and so on, up to the u acting on the last components, and everything else is 0. I mean, the components are not mixed. Different components are not mixed among themselves. It's only the same component of x and y are mixed with the u. Yeah, okay, but u is a unitary. I mean, u times u star is equal to 1. I mean, that's just a unitary which does a rotation. And of course, I mean, u star is rotating back. And u times u star is equal to 1. So this is unitary transformation, which means in particular it preserves length and angles. Okay, yeah, but then, I mean, so u star, or transpose maybe, is equal to 1. And of course the same is true for this matrix, which just consists of several u's. Okay, and now we know, so we do here a transformation, we act with a linear transformation on our Gaussian vector, and in assignments we have checked what this means. We get again another Gaussian vector, and in general, of course, the covariance matrix will change by conjugation with the transformation we are doing, but in this case here, this has no effect. So, and thus, by the behavior of Gaussian random vectors under linear transformations, and this was in the last assignment, just the exercise number 4, where you should check such things. We know that the new vector t1 theta s1 theta tp theta sp theta has a distribution which is given by taking the old distribution, on this side, but on this side it was just the identity, it was just N0 identity. And then of course we are not acting on the means here, so these are not going to change. But then with we are acting with our transformation, and maybe let me call the whole matrix here V. I mean U is a 2 by 2 matrix, and putting all these U's together so that I have an action on all components. Maybe let me call this matrix V. And I mean that's the matrix which acts here. And then if I'm acting with a linear invertible matrix V on my Gaussian vector, then here the change is that I get here V and V transpose, conjugation by V. Good, but now, I mean here's the identity, so what I have here is just V times V transpose, but now because this is an orthogonal transformation, then this is just the identity. So U times U transpose is just 1, because because just cosine squared plus sine squared is always 1. That's just the main point of this. So this here is 1. So what I have here is just the same as before. Nothing has changed. So I still have here a random vector which has this distribution, and this is just telling me that this is a vector where all the components are independent and each has a standard Gaussian distribution, and this means I have, so if I split it again into two vectors, x theta and y theta, each of them is a standard Gaussian, but they are also independent. So I mean, x theta, y theta has the same distribution as x and y before. So this means we have for each theta again a standard Gaussian random vector in R to the 2p, or this means if I'm splitting my big vector in R to the 2p in two vectors in R to the p, then each of them is standard Gaussian and they are independent. That's exactly what I'm claiming. Okay, so that's just making this lemma here precise, and now we can use this and continue with our proof of our concentration estimate. I think now we have more or less everything together. So I mean, essentially Jensen's inequality was an important ingredient, and we are going to use it again. And this property here is important. Okay, and this property here is really something which only applies to Gauss. I mean, Jensen's inequality, of course, is much more general. Their Gaussianity was not the issue, but here, for this part here, Gaussianity is really very important. Then let us continue the proof of our main theorem. 3.2. So now we continue the proof of 3.2. And let us recall where we stand there, and then use this. Okay, so what we have to estimate. So let me say it again. In principle, we want to estimate the expectation of the exponential of lambda times f of x. Good. Okay. In order to deal with this, we introduced this y, so we estimated this in the first kind of more trivial step against the same thing where we replaced f of x by f of x minus f of y. Okay, and then we also rewrote this here as the integral over the derivative, where I also choose a path which connects x and y. So this I'm also writing as the expectation of the exponential of lambda, and then this difference of x and y I'm writing as the integral from 0 to pi over 2 of the derivative with respect to theta of f of x theta d theta. Okay, yeah, okay, and this derivative here, of course, with the chain rule, is the outer derivative, so the gradient of f at the position x theta multiplied with the inner derivative, which is x prime of theta. Yeah. Okay. And I mean, gradient. This is a vector, and this is a vector. So this is the inner product between those two vectors. And let me recall. I mean, all the objects which we have here. So where we have the following. So first, our f. F, of course, is a Lipschitz function, but we also assumed it is smooth, and this means we have an assumption about the gradient. So f without restriction, or we can reduce the general situation to the smooth situation. And of course, our function is always Lipschitz with the constant L, but in the smooth case, this can be rephrased as saying that the gradient of f at any point is bounded by L, the length of this. Okay, then x, our vector x, is a standard Gaussian random vector, and y is an independent copy of this. So y is just introduced for the purpose of the proof. So y is an independent copy of x. So y is an independent copy of x, and then here we introduce this interpolation between x and y by introducing x theta as cosine theta y plus sine theta x. But then we also need the derivative of this, but the derivative of this is exactly what I called y theta there. So I also have here the x prime of theta, the derivative, I mean, this is the derivative with respect to theta, so the cosine is minus sine theta of y plus, and the derivative of the sine is cosine theta of x. And so we know that this pair of x and x prime is, for any theta, again, independent pair of standard Gaussian random vectors. I mean, that's what we just did in this lemma. Thus, by lemma 3.4, the pair x theta, x prime theta has a normal distribution in standard normal distribution in 2p dimensions for all theta. Okay, so that's where we are. Yeah, and now we have to try to estimate this. And of course, I mean, what is our goal? I mean, in principle, in order to get a kind of Gaussian estimate, the estimate that the probability is e to the lambda squared, we should estimate this expectation of the exponential against lambda squared. So it should be an estimate lambda squared, because that's what happens for a Gauss distribution. So in principle, I mean, yeah, if you want your concentration inequalities essentially in the moment generating function, so this exponential of expectation of the exponential of lambda times your variable, you should get something like e to the lambda squared. That's the best thing, because then you can get good estimates. So that's where we want to go. Yeah, but for this, yeah, we have to estimate this here somehow. And first, yeah, we Okay, so I mean, we know something. I mean, if this x theta, oh, okay, so we have here something. The point is, I mean, here we have a Gaussian vector. So this has a Gaussian distribution, and if we would have, maybe this is just, and this is a coefficient which we can control, or maybe let me say it in a better way. What I have here, if I'm fixing x of theta, then I have here a vector multiplied with a Gaussian vector. And if I take a linear combination of independent Gaussians, I get again a Gaussian. Okay, so this fixing x of theta, this is a Gaussian vector, and so if I have e to the lambda to this, then I could control it. So what would be good if I could bring this exponential here to this guy here. Because then I could use estimates for Gaussian distributions. And that's the first step what I'm doing. So namely estimating in the right direction the exponential of this against something where I take the exponential up to here. And this is just again Jensen's inequality, but now applied to this integral here. Because Jensen's inequality is for averaging, taking the expectation with respect to a distribution. I mean, essentially it's saying that the average of an integral is less than the integral of the average. And I mean, here we're integrating from 0 to pi over 2. This is just taking the expectation with respect to this measure, but I should make it to a probability measure. Because, I mean, it's really important in Jensen, I need a probability measure. So I should divide here, I mean, the integral from 0 to pi over 2, this has total mass pi over 2. So I should normalize this so that it is a probability measure, and then I just can apply Jensen again for this specific situation, which allows me to estimate this here. I mean, this expectation doesn't play a role at the moment. I just want to bring this exponential to this guy here. Okay, so that's what I'm doing now. So we use again Jensen's inequality. Now, for an average of the form, so I'm integrating from 0 to pi over 2, let's say a function g of theta, an arbitrary function, but I should average over probability measure, so I should normalize this, so I should here divide by 1 over pi over 2. Because I mean, if I'm integrating here over the constant function 1, I get pi over 2, but I should get 1 for probability distribution. Okay, so I'm using Jensen for this averaging and for the function, for a convex function. I mean, of course, for Jensen I need a convex function, but the exponential function is a convex function. So, and convex function h of t, this is, let's say, the exponential c times t. Okay, so this means what I get from Jensen's inequality is, let me write it down in this setting. So this tells me that my function, so the function of the average is less than the average of the function. So I take exponential, I take my convex function of the average, so I take exponential of c. C is here constant, which, okay, I will adjust to what it is there, and then I have to take the average, 1 over pi over 2, the integral from 0 to pi over 2 times some function in theta, d theta, so this is the convex function of the average. This is less than the average. Okay, so the average is now 1 over pi over 2 integrated from 0 to pi over 2, and now I have here my function applied to this guy. So I have here the exponential of c times g of theta d theta. Okay, so that is what Jensen is saying me in this setting. And now, of course, the g of theta is this quantity here. So I'm using this now for g of theta. This is the gradient of f of x theta times x prime of theta. And the c which I have here, of course, I mean I have here, what do I have? Yeah, I have the lambda, and then I have introduced here this additional 1 over pi over 2, so I have to repair for this, so I have this here again to multiply with it. So the c is lambda times pi over 2. Okay. And then I get an estimate here, and then I also apply the expectation value. So I mean I have the expectation value. This is with respect to my Gaussian distribution. This is the integral over the density of the Gauss. But here I have used Jensen just with respect to this integral here. Okay, no, not with respect to this expectation here. Good. Okay. Yeah. So for this, so what we get. Yeah. Okay. So maybe I can continue here. So it's less than. Okay, so the expected value is still there, and now I'm estimating this exponential according to this here, where now I just use what I have here. So I get it's less than 1 over pi over 2, the integral from 0 to pi over 2, and then I get the exponential. And my constant there is lambda times pi over 2. And now my function g is exactly this thing here. So I have the gradient of f at the point x of theta multiplied with x prime at the point theta. So that's here the g of theta. And then I'm integrating with respect to theta. Good. Okay. So now, of course, this expectation, I mean, this applies to my random variables. So this has nothing to do with theta, but of course, this applies to those guys. Okay. So I can, of course, bring this out, and this expectation in the integral also commute, because everything is linear. So this is the same as 1 over pi over 2, or 2 over pi. And then I have the integral from 0 to pi over 2. And now the expectation goes up to this point here. So I take the expectation of the exponential function of lambda times pi over 2, the gradient of f of x theta multiplied with x prime of theta d theta. Good. Yeah. Okay. And now, so here, this expectation here, this is now with respect to the Gaussian, the underlying Gaussian distribution of x and y. Okay, but we have seen if x and y are standard Gaussian random vectors, then the same is true for those two guys, and they are independent. So I mean, essentially, so what I have here is for each theta. I mean, I'm integrating here over theta, but this quantity here, this depends. So for theta fixed, what do I have here? I have here a Gaussian random vector, I have here a Gaussian random vector, and they are independent. And I'm taking the expectation over this. So this means this expectation here is actually independent of theta, because it's just taking the expectation over a pair of independent Gaussian, standard Gaussian variables. So this means this expectation here, which I still have to estimate, but at least it's the same for each theta. So I mean, it has looked, I mean, I have x and y, and I'm connecting them by a path, and I mean, I have to know everything which happens on this path, but essentially, because for each theta, it's exactly the same. So nothing really strange happens there, because the pair is always the same kind of pair. So this is just the expectation of the exponential of lambda pi over 2, the gradient. Let's say for theta equal to 0, and for theta equal to 0, x0 is the y. So I have here, let's say, my original y, and this here is just, the derivative is just x. Okay, so this is just the expectation over the Gaussian distribution for the pair xy, and they are just independent Gaussians. Yeah, okay, and now I have to calculate essentially or estimate this quantity here. But now I'm really in a situation where I can say something about this, because now what I have here, I have to take the expectation with respect to x and y. Okay, so I have to integrate with respect to the density of x and the density of y, but x and y are independent, which means I can, let's say, I can fix y and then take the expectation over the x. Because they are independent, this factorizes. So, and for each y, I know, so if I'm fixing y, then I have here a vector, which is now, let's say, a constant vector, over which I average later. But for this argument, it's constant, and I'm multiplying this with a vector which has independent Gaussian components. So this means I'm taking here a linear combination of this vector with independent components, and if I take a linear combination of independent Gaussians, I just get another Gaussian, and I know also what the variance is. Namely, this is just the L2 norm of the vector which I have here. So maybe let me write it here. So for each fixed y, I know that the vector which I have here, the gradient, and let me see, I mean I have here the gradient of f. This is the gradient of f at this position. Okay, so I know, so this is a vector, the gradient of f, and now my Lipschitz condition tells me that this vector has length less than L. So f at any point, or the gradient of f at any point is always bounded by L. So for each fixed y is the gradient of f at the point y, and it doesn't matter what y is, the length of this vector is less than L. That's the Lipschitz constant. And so the gradient of f of y times x, this is a linear combination of independent Gaussians, so this is a Gaussian again, and the variance of this is less than the the length of this vector. That's just a simple property of Gauss. If I take a linear combination or a fixed vector times a standard Gaussian random vector, I'm getting a Gauss distribution, and the variance of this is exactly the length of this vector. Okay, and here the length of this vector is always less than L, so what we get for each x is a Gaussian distribution which has variance less than L, or L squared. Okay, the variance is the square of this. Okay, so so this here and this is a Gaussian variable, a one-dimensional, with variance less than L squared. Yeah, but then I'm really now back to something which I can do, namely then I have here, so for each fixed y, I can do the expectation over the distribution of x. X has a Gaussian distribution, but then if I look on this, what I get is a Gaussian variable with variance less than L squared. So I'm taking here the expectation of e to the lambda times a Gaussian distribution. And that's something which at least in the case for standard Gaussian, I already showed you, but of course, this is something yeah, which is easy to see. So I mean, okay, maybe. So if let me see, if x is a normal distribution, one-dimensional, with sigma squared, then the expectation of e to the lambda x, this is e to the lambda squared sigma squared. Maybe a factor 2. I'm not so sure about this, but essentially it's this one. I mean, I get here e to the lambda squared. That's really what I want. I mean, that's what I really want for my overall estimate. But I'm using this now deep buried in the proof. That in the proof I really have Gaussian, one-dimensional Gaussian variables for which I know this estimate, and then I'm just integrating everything up. Okay, so with this, I get then that if I'm taking, let's say, the expectation, the expectation here over x, but for fixed y, then I get an estimate like this. So maybe let me write it down. So if I'm doing 1 over 2 pi to the power p over 2, integral r to the p. So let me write the expectation maybe in a explicit form. So I mean, the expectation I'm doing here is the expectation with respect to x and y, with respect to the densities, which are e to the minus norm of x squared over 2 for x times e to the minus y squared over 2 for the y. And then I'm just doing iteratively. By Fubini. I'm just fixing y and first do the integration over x, and then for this I can use this here. So for this, so I have the exponential of lambda pi over 2 gradient f at the position y multiplied with x, and then integrated with the density of the x, so the Gaussian distribution. This is then less than what I have here, and I think here I have a factor 1 over 2. If sigma squared is the variance, so I get here less than the exponent 1/2 lambda squared, and then it's getting multiplied with the variance of this thing. I mean, this here is less than L squared, but then I also have this extra pi over 2 here, so I get altogether here a lambda pi over 2 L squared. Okay, so I get this for each y. Just because this, if I'm fixing y, this here is just a constant vector multiplied with a Gaussian vector, which gives me a Gaussian vector, and the variance of this Gaussian vector depends on the length of this guy, which I can bound by L. So I get something which is the length of this, but I can always estimate this by L. So I get this. Okay, and so this means in this expectation here, I have now done for each y, I have done the integration over the density of x, but I get an estimate which is independent of y, because I mean y, only property, I mean y didn't really come into it. It was just, I mean f of y is everywhere I can estimate it. Okay, and now I can just do the remaining expectation over the y, but of course then this doesn't change anything, because for every y I have the same result. So integrating this now over the density with respect to y gives me then more or less my final estimate in terms of lambda for the quantity which I really need for applying my Markov inequality. So now I do the integration over y, and then I get that I can estimate the exponential expectation of the exponential of lambda f of x. So this thing, but this I have estimated against this, and now I have estimated in this expectation for each y, I have estimated this against this term, and now I'm just doing the remaining integration. Then I just get again this term, because this was for each y. Integrating over y with a probability distribution doesn't change anything. So I get exponential of 1/2 lambda pi over 2L squared. Okay, and that's what I was after. I mean, that's the main step which I have to do if I want to apply my Markov inequality. I mean, I still now have to go on and choose the optimal lambda. But what I really want is for this quantity, I want an estimate, and the best thing if I can get a lambda squared here. Okay, and now we just continue in the same way as we did it before in a linear case. I mean, also in a linear case, when the f was a sum of things, it was much easier to arrive at such an inequality. Okay, but now we can continue in the same way. So namely, what we really want is the probability that f of x is bigger than alpha. Yeah, and let me recall, by Markov, I mean, this is the same as saying that e to the lambda times f of x is bigger than e to the lambda alpha, and we apply Markov to this, which means we have to take the expectation of e to the lambda f of x divided by e to the lambda alpha, e to the lambda alpha. Yeah, but now for this we have now got our estimate. This is less than e to the 1/2 lambda pi over 2L squared divided by e to the lambda alpha. Or maybe this is of course now the exponential of 1/2. Let me take out the lambda squared, because lambda is now the variable which I want to optimize. I mean, this is true for all lambda bigger than 0, and I want to optimize now. I'm free to choose a lambda, because of course lambda does not show up on this side here. I have introduced this in an artificial way. This is inequality for all lambda, and here I have p over 2L squared minus, okay, this is minus lambda alpha. Good. Okay, and now I want to optimize this, and of course the optimal one should give me something here which is negative, because the probability I would like to have something like e to the minus something, and I'm choosing the lambda for which this here is the minimal value. So I just choose the extremum of what I have in the argument of the exponential, and of course this is very easy to do. Yeah, so I minimize now this side here in lambda. Let me call the minimizer lambda 0. So I should take the derivative, so it's 1/2 times 2 then lambda. Let me call it lambda 0, is the one for which the derivative is 0, multiplied with p over 2L squared, and the derivative this side is just alpha, so the difference should be 0, or this should be equal to alpha, or these 2 goes away, so the lambda 0 should just be alpha, maybe bring this on the other side, so it's 4 over pi alpha divided by L squared. So that should be the best choice of lambda, which I can do here, and then I plug this in, and then I get hopefully what I want. Yeah, So what is then this 1/2? Pi squared, yeah, okay, yeah. Should be, yeah. So, yeah, okay, yeah. So it should be pi over 2 squared brought to the other side. Good, but let's plug it in. So 1/2 lambda squared is now, okay, 16 over, okay, pi to the 4 now, the square of this. Yeah, the square of this is alpha squared divided by L to the 4. That's lambda squared. And then we multiply it, of course, again with pi over 2L squared, L2 squared. Good, okay. And then we are subtracting lambda times alpha. So it's 4 over pi squared alpha divided by L squared. And we multiply it with an additional alpha, so we get alpha squared. And you see it's good. We really get here alpha squared. Okay, and here on this side, we also have, yeah, maybe, let me take out the alpha squared. And what remains is, okay, the 16, oops, 1/2. Okay, I have here 2 to the 2, this is 4, this is 8 from the 16, there remains a 2. Pi's, I have here pi squared, I have here pi over 4, so I have a pi squared, and I have here an L squared. What happens to the L? The L was, there was no square here. It was pi over 2L. Okay, so this is just together an L squared with this 1 over L to the 4. I have a 1 over L squared in the bottom. And here I have actually the same, but just a 4 instead of a 2. So I have minus 4 divided by pi squared L squared. And so what I get is really, this is the bigger term, so I get a minus. So I get really minus 2 times, so 2 minus 4 is minus 2, minus 2 pi squared alpha squared divided by L squared. Okay, and so this means we get, for this, we get an estimate where this here is given by this. And this is more or less what we wanted to prove. I mean, we have an alpha squared divided by L squared, and then, I mean, this is not the optimal constant. One can improve this a little bit, but then one has to use different proofs, which is getting more complicated. But I mean, it doesn't really matter so much what I have here. The main point is to see that I have here really a decrease in alpha squared, and also to see how it depends on L. Good. Okay, so maybe, so what we see here is that the probability that f of x is bigger than alpha is less than the exponential of minus 2 over pi squared alpha squared divided by L squared. Okay, so that's our concentration inequality which we have in this setting. But of course this is quite specific for Gaussian distribution. And maybe I want to make a few remarks going away from this, because I mean Gaussian distribution is of course very special, so one would like to have estimates also for other distributions. I mean independence is okay, mathematically it's okay. I mean you cannot go really too far away from independence. So you need independent random variables, but the distribution of them, I mean usually, okay, it's not necessarily Gauss. So let's see what we can do, or what is there in general. And maybe let me also come back to the linear situation first, because I already addressed this when we did this, because there actually, I mean, the tools usually go much further. In this setting here, one can also generalize things, but then one needs more assumptions. Huh? So I want to talk a little bit about this. Good. Okay. So time is over for today. So next time I will write down maybe just a statement of general concentration inequalities in this setting, or say a few words about this, and then maybe also make one more remark about the non-linear case, because there things are getting a bit more complicated, and there is maybe a famous Talleyrand concentration inequality, which at least I also want to cite. Okay, but maybe today time is over, so maybe so that's it for today.